Hi everybody. So here is my promised recorded lecture for this week, which will again return to the diversity of arthropods. But we will start, as I indicated already last week, to touch some more general topics. So you may remember that in last weeks we went through different groups of arthropods, different groups of crustaceans, insects, spider-like things, and so on. And we were talking about their special ways of life, their special morphology, how they look like, and so on. So this is naturally also part of diversity. This kind of reflects their evolutionary history, that they evolved independently from each other for a long time. But now we will actually switch to topics which are kind of different, which are more general, not kind of covering different aspects of diversity than the evolutionary history. So the question for today is actually how many arthropods do live today? Yeah, so I mean really today. Now we can forget all the fossils and these things we were talking about. So the question only is, if I count today all the species living on our planet, how many will this be? What will be the number? You can remember that I showed you some pictures like that already before, and we were discussing that arthropods are actually the most successful group of organisms on the Earth. And correspondingly, the number of species we know about of them is much higher than for all the other groups. The important thing, however, was that these numbers I was telling you are the numbers of named species. That means the species which somehow somebody studied and put or give them the scientific names. But you can imagine, even if you go here in Taiwan to the forest, you will very easily, very quickly discover some species which has not been seen by anybody before. Some small beetles, some nice big butterfly, it can be anything. You can actually also discover totally new species which people either haven't seen before or just overlooked, even in Europe. So it's not that rare thing. So the question is, okay, so these things are just the species having names, but what is the real number of species we can find on our planet, right? So naturally you can guess that it's probably more than named one, right? But how much more? This is how many times more? Is it like twice that much or 10 times that much? So this will be the question for today. We will start not on the global scale. We will not think about the complete planet, but let's start in a very small setting. So I can ask you to give me the number of butterfly species living in our university campus. And the question is, and you would be asked to kind of invent some smart way how to do it, right? So how would you do it? You would probably go out, right? And you would collect some butterflies. So imagine that you would just make a simple graph, basically pointing or drawing the species which you collected. So for the on one axis of this graph, you will have the specimens, how many butterflies you collected, and on the other axis of the graph, you will have the species. So for the first thing you would collect will be some species, right? So you will have in one specimen, you will have one species. That's fine. You will collect another one, so you will have two species in total now. You will collect another one, and this will be still another species. So there will be three species of butterflies already. And you will collect another one, but naturally, time to time, you will collect the same one, same species which you already collected before. So here, even though you add the specimen, you don't add any new species, so you still have three. You collect more, so you can have another thing. This is another species you haven't seen before. And you can collect again, but again you collected something which you already have seen before, so we will just add number of specimens but not number of species, and you will collect again, and again you see that even your seventh butterfly you collect is the same which you have already seen before, right? So you will actually have the points in the graph, and you can see that you can make something like a curve through these points, and this curve is in the beginning growing quite quickly, but once you collect more and more, you will actually start collecting the species which you already have seen before more frequently, until the moment when you actually only collect the things which you already have seen before, and the curve starts to be kind of flat, right? So it goes to the plateau. And then you actually can guess that this is the number of species which really lives in our campus, that you basically did not overlook any of them, and you collected enough specimens to basically recognize or record every species living in the campus. Right? So this is one possible way how to figure out whether you actually need to collect more or whether what you have actually is already enough to give me the number. So in this case, we basically just keep collecting more and more and more specimens, and we kind of try to estimate whether what we collected is already more or less complete or whether we actually need to collect more. We can do also another tactic. So we can actually go around and either collect or observe the butterflies and basically put in the graph how many species we have seen every day, right? So this time the one axis will be the days which we do the kind of exploration, and the other axis will be again the number of species. So imagine that the first day we will see 4 specimens of butterflies, but they will belong to 2 species only, right? So in my graph, I will have day 1, and I have seen 2 species in total. In the second day, I will observe 5 different butterflies. They will belong to 3 different species, but you can see that I have already seen the yellow one the day before. So that means that in total I have seen 5 species now: the red one, the yellow one, the gray one, the green one, the purple one. And I have seen them in 2 days of fieldwork, like the 2 days going out. The third day I will see 6 different butterflies when I go around, and these will belong to 1, 2, 3, 4 different species. But you can see that I already saw all of these species before, right? So for the third day, we will actually not change the kind of complete number of species, the total number of species I have recorded for the campus. I can continue that way. So maybe this fourth day, I will see 3 specimens of butterflies. 2 of them, 2 species I already saw before, but I will finally record something new, the blue one, right? So in total, I have seen 6 species now, and this is for the day number 4. I can continue, so in the next day I will observe these butterflies. You see again that I saw all these species before already, so for day 5 I will not add any more species, so I still have 6 species in total observed. And for the day 6 I can actually I also did not see more species, so I still have 6 in total. For the day 7 I only discover 3 specimens. Each of them belongs to different species, but I already saw all of them. So again, only 6, right? And again, we can make something kind of like a curve through these points. And you can see it looks a little bit similar to the previous one, right? So it goes first quickly up, and then it kind of makes the plateau, the kind of flat thing. And here you can also see that basically, probably based on this very quick thing, I can guess that probably our campus has 6 species, because even though I go out more and more days, I can still only discover the same species which I have seen before, nothing new, right? So this would be kind of the way how we normally do it. Because we always in these curves put on the y-axis the total number of species, and this number of species somehow accumulates over the time. So it's the total number of species we have observed through all the research, all the project. So this thing is called species accumulation curve. So this is basically how number of species accumulates once you collect more and more and more, right? And we can actually see that first always this curve goes steeply up, and that at some moment it goes flat, and this kind of indicates that we already reached the real number of species living in the area, and we can kind of estimate, okay, in our campus we have this or that number of species. So once we see that in our data, we can see that we collected actually enough. We collected enough samples. We went out for enough number of days. We collected enough number of specimens to make to get some number, right? To get the result, how many species we have in the campus. Also, notice that we can do it in two different ways. So my two examples actually did the same thing, just in two slightly different ways. In the first example, I was counting every specimen, right? So specimen means individuals. And in the second example, I was actually counting as one thing every day. And in this case, it would be something like a sample, right? So you go out, you collect or record everything you saw in this place in that day. And that's your point, that's your one number or one piece of information. So once we have the individuals, once we go by individual specimens, we naturally need to know the number of them, right? So we need to know how many specimens of which species we actually collected. Once we go for the samples, we actually kind of don't care. So you can notice that once I first day saw 3 specimens of the yellow butterfly and one of the red one, I did not care. I just put in the graph that I saw 2 species in total, right? So in the second case, we actually ignore how numerous, how common are with species. We just put there basically the fact whether the species is present or absent. So this is so-called presence-absence data. For the data which count the specimens, counting the specimens, how many we have of them, is called abundance. So this is the data which we use as the abundance data. Okay, so how it actually looks like in the real study, because our example naturally was a little bit silly. So what if we go out and we really try to do it for the butterflies, right? So there's a study in Malaysia, so in some national park. They collected at 3 different altitudes, and they basically did the similar thing which was in my first example. So they collected or observed the butterflies, and here they go, as you can see on the x-axis, they go by the individuals, right? So this is this abundance data. So every individual is on the x-axis, and you can see that in all 3 cases, the curves still go up. You cannot really see that flat thing of the curve, right? So what that means? That actually means that they would need to collect more and more specimens to get to this flat area and to be able to give me the number of butterfly species living at each altitude, right? Similar thing can be done or have been done in different groups. So here's another example of the beetles in one national park in Ecuador, in Amazonian forest. And here you can see something similar. So in both cases, the curves still go up, right? You cannot see any flat thing. So again, this basically means that, okay, we can have some idea, but in reality, our data still miss many species, and to really record, to really collect all the species living in the area, we would need to collect much longer. Here you can notice that the x-axis has the samples. So in this case is this data like presence absence data in the samples. So each thing on the x-axis is basically one collecting thing. They go out, they collect some leaf litter or something, and they extracted all the beetles of this group from that, and they just recorded, okay, in this sample we have, I don't know, we have 15 species, and we in total with all the other samples seen before already have, I don't know, 55, for example. And this can be done for anything which you would like to estimate. So here's another example, not for insects this time. So we can actually go to the fish port here in Taiwan. So the closest one we have to Kaohsiung is in Donggang, south of Kaohsiung. It's not that far. You can just drive there the motorbike in half an hour. And the fishermen actually go out to the sea every day, and they return around lunchtime, They bring all the fish, which then they sell on the market, which is next to the harbor. But they also accumulate all the other animals which somehow were collected in their nets. They call it bycatch. They naturally don't need them because this is not what you can sell, right? So they accumulate them in piles, and you can actually go there. This is how I got some of the crustaceans we have seen during our practical part of the crustacean lectures. And you can examine what they collected, and you can do something similar. You can just for every day see how many different things they collected in some groups. So let's say this study which I am showing to you was done on crustaceans. So the people from the university went there, and every time they went through all this material and they recorded how many crustacean species they actually had. And once they did it many times, so here you can see that they visited the harbor 30 times. They again can make the curve, and the curve will naturally not look that nicely smoothly as it's the kind of black lines in the graph. The curve will be something like the red line, and you can again see that the curve still goes up, right? So even after visiting the harbor 30 times and checking all the catch of the fishermen, you actually can be quite sure that there are still some species of crustaceans which are living around, but you still haven't seen them. You still haven't find them in the samples because you are still discovering new and new species. Your curve is not flat, right? So this is very general kind of way of thinking, and we can use this method for any kind of estimate or any guess whether what I have already seen and collected of any group of organism doesn't need to be arthropod. Naturally, it can be any organism you study. Whether what I have already seen is actually all the species or not. Okay, so basically. That means the real example I have shown you, all of them the curves still go up, right? So that basically means that in real cases, we very rarely collect all or most of the species. So that means that we very rarely reach this part of the curve which is flat. Why? Why is that? It's because we don't have that much time. It would need really lots of time. It would need really lots of money, right? So you have to go to the forest. You have to pay for traveling, accommodation. You have to go with students, pay them. You have to pay alcohol for preserving the specimens. You can pay the vials. And you would also need lots of time to identify them. And on the other hand, you would also need to kill many specimens, right? So we usually don't really have the luxury to do all of that, and we don't want to kill that many things. So we actually have to rely on not collecting everything, but somehow estimating how many things live in the area, even though we haven't collected all of them, right? We use our incomplete data to somehow estimate how many species live there. What is the complete number from our incomplete data? So how to do it? There were some early attempts for that. The first one was published in 1993, and these guys actually realized that actually this observation or these points we have always make the curve, right? So this was the curve the species accumulation curve which I have shown you. So if we want to know what is the total number of species living, let's say, in the around the harbor of Tonga, we would need to kind of estimate how will the curve continue when we add more and more species, right? So we have our data only for 30 samples in this case, but we would like to estimate somehow how will the curve continue if we add more. This can be naturally done, and one way to do it, you know probably that each curve has something like mathematical formula behind it, right? So we would need to take our real data and try to figure out which mathematical formula is actually behind this curve. You probably know that this is the same principle as there's this mathematical joke of what is the equation of love, right? So the heart shape actually can be also drawn or described. The graph of this shape can be described by some mathematical formula, some mathematical function. So the logic is the same. We would have some curve. We know part of this curve based on our real data, and we want to kind of know how this curve continues. That means that if we estimate this mathematical function, we can kind of know how it will look in the kind of adding more specimens or samples, right? The problem is that very quickly they realized that different functions, you can use different functions to kind of describe what we observe, the real data. So all these three functions, function 1, 2, or 3, basically would look the same in the beginning, right? So it will really kind of describe what we observed, our real data, nicely. But then they actually differ quite a lot in the shape for more and more samples. So function 1 would give us much higher estimate of the species than function 3, for example. So this was somehow figured out that it's not probably the best way, or at least it cannot give us some very reliable estimate, right? So this kind of logic, how to figure out what is the total number of species from how the species accumulation curve will continue based on the mathematical function, is called parametric diversity estimate. This is because in any mathematical function, for example, here I put the y equals 2a plus b, this a plus b are called parameters. So you would actually need to know the function, know the formula. The formula would include some parameters, and based on that, you would be able to estimate the diversity, the total diversity of species, right? So because we have parameters inside, it's called parametric. But it's actually hard to use, especially if our real data are not really going close to this flat part of the accumulation curve. This way actually cannot give us a good estimate. So we would need to try to figure out some trick, right? This kind of pure mathematical way doesn't really work that nicely. So how to do it? So if you return to our example of the butterflies observed in the campus to figure out how many species are living in the campus, you can imagine that you can notice that we actually used only part of the information, right? We only used to make the curve. We only used the number of new species we observed every day. So for the first day, we have seen 2 species, right? So we put the point from 0 to 1 to 2. And the second day, we have seen 3 new species. Right, we have seen the yellow one already, so this does not count. We only have seen the green, gray, and purple as a new one. So this is the +3 which we add. And the next day we haven't seen any new species, so nothing, just +0. And the next day we have seen 1 new species we did not record before, so the blue one. And in the days after we haven't observed any new thing, right? So we basically just use the how many new species we observe every time we go out. So it's very small piece of information. So if you can imagine that I will make something like a table, something like an Excel sheet, and I will put for every day which species we observed. So for example, you can see that the red species we observed on the first day, on the third day, of the fourth day, of the fifth day only, right? The blue species we only observed on the day 4, for example, so we can make a table. So for our graph, we actually only use the information when we observe this species for the first time. So this red thing, this red yes, this is the part of information we used for making the curve, right? And we totally ignored all the green ones, all the other information actually when we observe the species again. So the question is, can we actually somehow include this data? And can it help us to make our estimate a little bit nicer? you can notice that we actually, if we look at the data in total, you can notice that we have some species which we can see and observe nearly every day, right? So the red one and the yellow one, basically we have seen them most of the days when we went out. And then we have some other ones, like let's say the gray one and the blue one, which we have seen only once. So we have some common species, which we see very often, and we have some rare species, which we see very, very rarely, very infrequently. This is actually the information which can be quite important to make us guess whether what we get is kind of fine or not, right? So imagine that I have two tables for two different places for these butterflies. The first one, place 1 is on the top, place 2 is on the bottom. And the question is, for which place do I need to collect much more to get good idea about how many species live on this place? What would you guess? You are not in person next to me, so I cannot ask you, but the correct answer is that for the place 2, for the bottom one, we would need to collect much more. Why? So in the first place, in the place 1, you can see that we actually have many species which we collected many times, right? We have seen them more than once or twice. That actually means that probably if I recorded the 6 species, I probably did not miss many others, because in my place there are actually not that many rare species. Already during the 7 days I start to see many of them and again. So probably the number of rare species in this place is quite low, right? So I can be, even after 7 days, quite close to the total number of species living there. But in the second place, you can see that most species we have seen only once or twice. So all of them are rare. And that actually means that there can be many more rare species living there, right? Because if there are 6 rare species, that it can mean that there can be 30 other rare species. And because you can only see them once in 7 days, let's say, or some of them even once in maybe 1 month of observation, that we probably missed many of them, right? So based on how many rare species we have, we can actually somehow guess how close we are, how much more work we need to get the data, kind of estimating how many species, or to collect the data which give us some reliable estimate or reliable information about how many species live on the place. So that means that rare species are really important for actually estimating the number of species living on the place. And this idea was first somehow worked on by Professor Chow. So here's the very important trace of Taiwanese research on this diversity kind of branch of research. So she's still working at the National Tsinghua University in Hsinchu, and she was first in touching this topic in 1987. Later, she worked on that a little bit more in 2000, and actually she's still publishing some updates for new methods of recognizing species or working on, including some DNA metabarcoding and so on. So how we can apply these methods and correct them for new types of data. She's still very active. And she first touched something which we call unseen species problem, right? So basically the idea is that once we go out, let's say to our campus, trying to figure out how many butterfly species we have there, we will see some species, we can collect them, but there will be always some number of species which we haven't seen, right? Maybe because they are rare, or maybe because we went out only very few times. There can be many different reasons. So, and her question was, is there some way we can estimate how many of these unseen species are living on the place? So she kind of applied very, very nice and simple logic. She kind of showed it mathematically, which is for me totally not understandable. But the logic is very simple. We don't need any mathematics for that. So she basically shown that we should not look only at the total number of species which we go once we collect more and more and more samples or more and more and more species, but we should also look at the number of species we have in our data as one specimen only or seen only in one sample, and number of species which in our current data we have only seen in two specimens or in two samples. She called it singletons for those which are only seen once, or doubletons which are only seen twice, right? And you can imagine that if we have a complete inventory, so we collected long time ago, a long time, so that we really have all the species which live in the place, that we would our species accumulation curve, the total number of species, the blue one, will become flat, right? And in the beginning of the study, we will have very many species which are rare, the singletons, which we only have one specimen. But once we collect more, we will start to slowly collect them again, even though they are rare, until we reach the moment when we actually have all species at least in two specimens, right? So we have no singletons. This red curve will go to zero. And the same will happen with the doubletons, with the species we only have in two specimens or in two samples. If we collect enough, and we really kind of can be sure that we noticed all the species which live in the place, we will probably have no species only in two samples. We will have all of them at least in three samples. So even this curve, this green curve for doubletons, will over the time, with adding more and more specimens or adding more and more samples, will go to zero, right? So if we have these three curves like this, we can be totally sure that our inventory, our kind of research of how many species are living in the place or in the area, is totally complete. We know all of them, but we basically nearly never have it, or basically I haven't seen any study having that, right? So we never reach that point. Usually we have something like this. So we have not that many samples, right? So that's why actually my only what I did, I cut kind of the x-axis. So we have less samples or less specimens examined. And you can see that our total number of species curve, the accumulation species curve, the blue one, starts to kind of be nearly flat. And the curve for singletons and doubletons kind of starts to go down, right? So this is incomplete naturally. We haven't seen all the species. We haven't collected all the species living in the place, but our data are good enough, large enough to actually estimate. We don't need to collect more. We can very easily estimate how many more species are there which we haven't seen. And then we can actually have the study like this, when all these three curves still go steeply up. And the only information which this can tell us is that our study is still very incomplete, right? We don't have enough data. We still need to collect more to get data which are good enough to let us to estimate what is the total number of species living in the area. So if you actually remember some of these real data which I showed you in the beginning, most of them had something like this, right? They have still this blue curve going steeply up. They did not really try the singleton curve and doubleton curve, but if they would they would actually also have them going very steeply up still. So their studies were actually very incomplete, and they would need to collect more to get better data. So Professor Chow, based on her mathematical skills, she actually made a formula for how to calculate this kind of total number of species, which is naturally the estimate. It's not the number which you say that, okay, it's like that. It's just an estimated number based on your data. And this naturally includes the species which we really observed or collected, which we really can find in our samples, plus some of the estimate of these unseen species, right? So you can see that her formula basically consists of putting everything which you have collected, but also adding the species which we estimate as being there, but we actually did not see them. We did not collect them. You can see that in this red part, in the estimated number of unseen species, the things which kind of is important for this number is how many samples we actually examined. Right? So in our butterfly case, it would be how many days we went out, for how many days we went out to observe the butterflies. Then there would be the number of species observed only in one day. So this would be this singletons. And then the number of species observed only in 2 days or in 2 samples. This will be this doubletons, right? So if we return to, and there are similar estimators with very similar logic for a little bit different kind of data or using a little bit different formula. The logic is totally the same. So if you see something like Chow 1, Chow 2, this is named after Professor Chow, or ICE or ACE. These are basically this kind of estimators of species, total species numbers, using totally the same logic. They put your species which you observed plus estimate how many of unseen species are there, quite probably. Because they don't use any graph, so they don't use any mathematical function which needs some parameters. These estimators are actually called non-parametric, right? So these are our non-parametric estimators of species diversity. So let's check how it works in our hypothetical example, which is naturally much simplified. Normally we need much more data. So just take it as a example of how it works, not as a real thing, real study. So for the first place, right? So we were comparing these 2 places, which of them has for which of them we need to collect more to kind of get the complete number of species. So let's say what these estimators would tell us about these 2 things. So for the first place, so number of observed species is 6, right? We have 6 species of butterflies. Number of samples is 7 because we have 7 days. How many singletons we have? That means how many species we only see once, right? We only see the blue species once. So we have 1 species which is a singleton. And how many species we have seen only twice? This is the doubleton. This is the species 5, the gray one, right? We only saw it in day 2 and day 7. So we have 6 observed species, number of sample is 7, and we have 1 singleton and 1 doubleton. For the place number 2, we have the same number of species and some number of days, right? Some number of samples. So this is the same. But the difference is that we have more rare species, right? So if you check how many species we only observed or collected once, this is 2. So this is the blue one, and this is the green one, the species 3 and species 6. And then we have 3 species which we have seen only twice, right? Species 1, species 2, species 2, species 4, 5. I'm not sure if I did not make mistake here, but let's imagine that it's 3. So how it will look like? It will look like this, right? So if we put these numbers in the formula on the top, we would get lower number for the place 1 and higher number for place 2. In this case, because we have a silly example, the difference is not big. But you can still see that the estimate for total number of species for the place number 2 is a little bit higher, right? So it still works, even with the stupid small data, which I just made up, it still works. So once we have more rare species, the number of the estimate of the unseen species will actually get higher. And that's why the total number of species estimated for that area will also get higher. Cool. So this is basically how we do it, or how we think about species diversity. Once our task is to estimate how many species or something are living in some area. It can be the campus, it can be the reserve, it can be, I don't know, the transect for bird watching if you do birds, it can be some coral reef. The way how we will do it would be always this way, right? We want to estimate how many species live in some place, we call it local diversity. But we can also kind of have a question about some larger area, right? So how many species live in the tropics? How many species of arthropods live in the tropics? Or how many species of arthropods or any other groups of organisms lives on the whole planet? That's a little bit more difficult task. So let's check how it is done. It started for arthropods with this paper in 1982, published by Terry Irwin, which was the beetle specialist working in USA in Smithsonian Institution in Washington. He unfortunately died last year, I think. But so he was a beetle guy, and he published a paper which only has 2 pages. And this paper started to be the most influential kind of paper about the species diversity because it started something, right? So what he did actually, he was a beetle guy, so he focused on beetles. He focused on special kind of part of the beetles living in so-called forest canopy. Canopy means the tree crowns, right? So this thing which is not on the ground, which you have to climb to the trees to be able to collect it. He did not really care that much about all the beetles, but for his estimate of number of species worldwide, he mainly focused on the beetles which are feeding on plants, so-called herbivorous beetles. And if something is feeding on some plant, you can imagine that some of the beetles can eat everything and some of the beetles will only feed on one specific plant, right? We will talk about that later. This is because to eat some plant, you need some special adaptation. Plants are doing many nasty chemicals to try to defend themselves, and also many other nasty things to prevent any attack by other organisms eating them. So it's not actually that easy to eat many different plants. Each organism, each insect eating the plant has to somehow have some adaptation how to deal with these chemicals or deal with the other defenses. So very many of the plant-eating insects or other things are actually only able to eat some of the plants. You know it even for people, right? Some plants are poisonous for us, so we also cannot eat all the plants. We only can eat some of them. So this species of beetles, which are only living in one species of plant, are so-called host specific, right? So they are very much specialized. They only can be found on one feeding plant. So what he actually did, he went to the tropical forest and he collected all the beetles living in one species of tree. He got some number. So his estimate was that he had 163 species of beetles living on this one species of tree in the tropical forest in Panama. Then he had some idea about how many number of tropical trees we have, right? So the estimate at that time, and I think it's still more or less close until today, was that there are something like 50,000 species of tropical trees. Naturally, not all the insects which he collected from that tree, from the canopy of that tree, were beetles, right? So he also needed the estimate of what is the proportion of beetles in all these samples. So he estimated that probably 40% of all arthropods living on the tree canopy of this tree are beetles. And then we also would need to know how to kind of estimate not only the canopy living things, but also include the things, the beetles living in other parts, right? Other parts of the forest, in the ground, underground, and so on. He would also need to know what proportion of all beetles living in the forest actually live in the canopy. So for him, it was 2/3. He was thinking that 2/3 of all beetles in the forest, in the tropical forest, lives in the canopies, lives high on the trees. So when he multiplied all these things, he basically got the number of 30 million tropical arthropod species. And he kind of also, naturally, it was known how many beetles are described compared to all arthropods, so he was able to use the estimate based on beetles to kind of extrapolate it for all arthropods. And I made a mistake. Sorry. So the third number is how many beetles is known compared to all arthropods. So the idea was that 40% of all arthropods are beetles, right? So he has number of beetles living on this one species tree, one tree in the tropical forest in Costa Rica. He knew how many species of tropical trees is existing on the complete planet. He had some estimate that beetles form 40% of all arthropods. So if we estimate the number of beetles and add another 60%, then we have the complete number of arthropods. And he also estimated that 2/3 of the beetles live in the forest canopy, in the high trees, and only 1/3 lives lower, just to include not only the canopy things, but include everything. And he got the 30 million estimate, right? So he was basically the first coming out with this kind of huge number. There were some estimates even earlier, naturally, but they never provided any clear way how they reached the number, right? So Erwin was actually the first one who used some kind of formula to reach some estimating number, reach the 30 million number. That means that his estimate was actually possible to be tested. Because, for example, you can go to that forest, you can collect on another specimens of the same species of the tree, and you will figure out that, oh, I did not find 163 species of beetles, but of the herbivorous beetles, but I found only 100, right? So you would be very easily able to test the final number, because if you find less, naturally the total number will get lower, right? So that's why this 2-page paper was so influential, because it for the first time provided some kind of clearly described way how we estimate the number of species of arthropods worldwide. Now the question is, so okay, when this was so important because it can be tested, so what is actually the thing which can be wrong, right? Because the fact that it can be tested means that, okay, some people probably question that estimate. So what can be wrong? So one of the things which he included in his equation was this thing that 2/3 of all beetles live actually in the canopy, live in the high trees. This was the effect, the reason why he estimated so much was because at that time the way how they collected all these insects was so-called canopy fogging. So you can actually make something like the insecticide, the special chemical killing insects. You can put it inside of the machine making the fog, and you can kind of fog the complete tree. Below the tree you put the white sheets, so all the insects which is killed by this fogging is falling down on the white sheets, and then you collect all of them, and you have many jars with the insects, right? And you can check what is there. This was tried for the first time in this 1980s, and people got super crazy, like how many arthropods, how many insects and other things were living there. It was not expected, because people were thinking, okay, there will be probably some insects, spiders, and other things living high on the trees, but nobody expected how much it is, right? So they got so much material that at that moment people were thinking, oh wow, this is totally unexpected, and actually there are so many things living there up on the trees that probably most of the organisms live there. So that's why his estimate for how many beetles live in the canopy was so high. The new data actually show that this is not that crazy, right? So there are some new data from Australian forests and some other places, which actually show that only 25% of insects are specialists for canopy, so are only living in high trees. Then we have 25 species more or less living more close to the ground, and some species, more than half species, kind of are more widespread. They live closer to the ground, also high in the canopy. They don't care that much, right? So actually nowadays we would guess that this number would be about 0.25, not 0.6, as he has in his original estimate. Another thing, so what is the proportion of beetles to other arthropods? He guessed that there are many more beetles than other things, so he basically guessed that beetles are 40% of all arthropods. But that can be also questioned quite easily, right? So for example, in this graph below, this is the number of known insect species in Great Britain. Great Britain is selected as an example or as a thing to consider here because it's the country where they know basically nearly all species living there, because the research on insects is done for centuries there. You can see that it starts something like in 18th century, right? So they do the research for so long, and also it's not a tropical country, so the diversity is not that high, that they can be sure that they have still they have quite good knowledge about the number of species. And you can see that for beetles, this is what is in the graph with the COL, like Coleoptera, the number of species is actually much lower than number of two other groups of insects, which are the Diptera, which means the flies and mosquitoes, and the Hymenoptera, which means the wasps and ants and these things. So this would actually indicate that we know more beetles than all the other insects because they are more studied. More people work on beetles than on flies, for example, right? Terry Irwin himself actually kind of very directly commented on that, and this is a quote, saying that if the microhymenopterids would get off their lazy asses, if they work harder and start describing species, they would be much more microhymenoptera than they are coleoptera, than they are beetles. Microhymenoptera, you can imagine, are very tiny wasps, mostly parasitic, mostly kind of laying egg in some other insects and having the larvae eating other insects. So there are probably many more species of these than of beetles. So probably his estimate that beetles form 40% of all arthropods was also a little bit exaggerated, right? So what is actually the reality? Based on this UK data, we would guess that probably the Hymenoptera, the bees and wasps, can be the most diverse. It's still actually not that sure, but there are some more and more papers indicating that Hymenoptera really can be the most diverse thing. The reason is that if you remember from last week, I told you that basically large part of this group, like large part of Hymenoptera, are parasites, right? We have seen the spider-eating wasp. We have seen the wasp which is actually paralyzing the cockroaches and laying the eggs on the cockroach. And many species of this group actually do something similar. So in the most extreme kind of case, we can imagine that every other species of insects has its own parasitic wasp, specialized only for this one species. And that naturally would mean that there's at least that many parasitic wasps as all the other insects, and parasitic wasp, or the Hymenoptera as the order, as insect order, would be the most diverse, right? Actually, it's probably not that easy. You can see in the picture on the bottom left that it's a little bit complicated by the fact that these parasitic wasps do not necessarily lay eggs only on one species of insect. Some of them do that, some of them are very specialized, some of them can actually parasitize on several different species of beetles and also of insects, and also sometimes the same species of insect can have actually more than one parasite. So this is actually making the thing a little bit more complicated, so we are still not really sure how to estimate it. But there are some hints, there are some indications that actually beetles are not the most diverse group, as we can guess based just on the number of described and named species. Another thing is, so how many species are only living, how many beetle species are only living on this one tree, right? So For Erwin's estimate, the first number was actually 168, was actually the species of beetles he guessed that they only feed. This was number of the plant feeding beetles, and this is the number of beetles which only feed on this one species of the tree, right? So they are very specialized. So this was also a little bit kind of questioned because Erwin actually supposed that 20% of all plant feeding beetles are kind of the specialist, right? So are only eating this specific tree. New data actually say that it's much less. There were many studies. It was actually kind of first time questioned by these two guys, Wojciech Novotny, who is the insect ecologist working in Papua New Guinea, and Yves Basset, who started big works in Barro Colorado Island in Panama. And they somehow questioned this kind of estimate of Erwin that so many plant feeding insects are specialists, and then other people added more and more data, and nowadays we know that there are actually there's actually much lower number of species strictly specialized on feeding one species of plant, right, in the tropics. So now the guess is something like 3 to 5% of beetles. So it can be something like 3 to 6 beetle species per each tree species. And another thing which we can observe from the data is there's a very huge difference between different studies, right? So if somebody studies one group of beetles in, I don't know, tropical America, and other person studies a little bit different group of beetles in tropical Asia, they sometimes get very different results. So it's very difficult to actually kind of make some one guess. Why is that? The reasons can be different, but part of that is that different areas are actually inhabited by mainly by different groups of organisms, right? So you can imagine that if you do the research, for example, of this group of beetles, it's called leaf beetles. It's one of this big group of beetles feeding on plants, and you will compare two studies, one done in Papua New Guinea, and the other done somewhere in tropical South America. Because in New Guinea, the main group or main diversity of these beetles is in the one subfamily called Eumolpines. You don't need to remember that, but just one part of them. Most of these beetles are kind of less host specific. That means that they usually don't really specialize that much into one single plant. It's because how they can digest the plant, it's because how their larvae are living, it's because of their lifestyle, their evolution, and so on. So for some reason, this group of beetles forming main of the plant feeding beetles, the main part of plant feeding beetles in Papua New Guinea, is not that specialized. If you will do the same study in America, and in South America, the most beetles which you would discover on the plants would belong to the subfamily called Alticinae, which is something like jumping leaf beetles. And in this group, for different reasons, many species are really host specific. That means that they only feed on one species of plant. So you can imagine that if you would compare these two studies, these two sites, you would get totally different results, right? So it would not be because because of your wrong studies or something, or wrong design of the experiment. It would be because you are on the different place and you're actually mainly looking at slightly different beetles. That's why we actually need lots of data all over the world to have some good idea how representative, how good are some kind of guesses of species numbers, or how things are specialized, how they live, how many insects feed on one tree, how many insects live in the canopy versus in the leaf litter in the ground, and so on. That can differ between America, Asia, Africa, and so on. And the only way around is actually to get more and more data all over the world, right? So we'd actually need data from different parts of the world, different regions, and also different types of the forests. This is the main reason why nowadays the researchers from all over the world started kind of specific places, specific plots, specific pieces of forests in different parts of the world. So you can see that there are some in South America and Central America, one in North America, one in Japan, many in China, some in Taiwan as well. I will show you some in Europe, some in Africa as well, which are a little bit blocked here, where many researchers actually study the forest there, and they accumulate similar data, and then they can more easily compare and kind of generalize things for the whole planet, right? So for example, there is a big initiative, big cooperation project of many vegetation ecologists and ecologists in general, which is called Forest Geo. It has many plots, many these pieces of forest which are studied every year by many researchers all over the world. We actually have 4 of these pieces of forest studied, so-called plots, in Taiwan as well. So one is in Fushan Botanical Garden, one is in central Taiwan in Lianhuachi, and 2 are in Kenting. And in these places, there are many researchers actually studying many things. So there are vegetation ecologists studying how the forest grows, what is the, I don't know, effect of typhoons on them, what is how they grow, what is the effect of local animals, and so on. There are many studies running, and similar studies are running in all the other places. So then we can actually take the data from all over the world and a little bit compare. As an example, naturally I cannot really tell you in detail about kind of all the places, but let's take an example, right? So there was a very famous paper published in, I think, Science or Nature, I don't remember now, about the San Lorenzo forest in Panama. So San Lorenzo forest in Panama, you can see on the map, it is somewhere in Central America. It is some quite small reserve. And they actually did not study the complete reserve, because that would be crazy. They only studied half of the hectare, or nearly half of the hectare, 0.48 of a hectare, right? To give you an idea of what that means, 1 hectare is basically roughly the size of the area of the rugby playground. So you can imagine that what they study is actually quite small. It was only something like half of the rugby playground, right? Very small area. They did crazy things. So the study actually in this forest took 9 years. For 9 years they were collecting, and more than 100 specialists, 100 people working on specific arthropod groups were identifying and identifying and trying to describe and name things, and to get the data for that. And they use different collecting techniques. So you can see that they also use this canopy fogging. This is the guy on the bottom left. Yeah, it is kind of making this poisonous fog, which is going up to the canopy and killing the insects, which would then fall down and are collected. They also collected in the canopies using some kind of cranes, which they built there. Or they even used something like balloons with hot air, which were kind of carrying the individual scientists higher, and they can collect there, as you can see on the photos. So there were many different ways how they collected. Naturally, they also collected on the ground, not only in the canopies. And as a result, they got the result of 6,144 species of arthropods living in this 0.48 hectare, half of the hectare of this tropical forest. The number is crazy. It's really much more than it was expected, right? Naturally, it goes even higher if it is kind of estimated for the complete reserve. So they did not really sample the complete reserve, but it can be estimated somehow. The estimate was 25,000 of species of arthropods, right? So in this one small reserve, which has 6,000 hectares, we guess that there can be something like 25,000 of arthropod species living there. Now you can be kind of questioning what I show you, because yeah, it's a little bit weird, right? So I tell you that in half of the hectare there are something like 6,000 species, and then I tell you that in 6,000 hectares there are 25,000 of species. It doesn't really make sense, because if every half of the hectare has 6,000 species, then if we have 6,000 hectares, we should have 12,000 times more species, right? Just by the area. But if you would just multiply these two numbers, which is what normal people would do, you can already guess that something is weird, right? Because we would just multiply 6,000 times 12,000. 6,000 is the number of species per half of a hectare. 12,000 is how many times half hectare, how many half hectares are in the complete reserve. And you would get the estimate something like 72 million of species. And that's even more than Evan estimated for the all species living in the complete planet, right? So something is wrong about that. What is wrong? The reason why it's not working like that is that when we start to study small area and then we kind of expand this area, we have a larger and larger area and we count all the species there, we will not have kind of linear kind of race of the species. So if you make the area twice as much, you will not have there twice as many species, right? If we know that there are 6,000 species living in half of the hectare, if you would study the complete hectare, you would not get 12,000 of species. You would get actually less. The reason is that naturally the species living in the next hectare are partly the same as living in your original one, right? So that's why once you kind of get larger and larger area, you will not get the number of species which accumulates, which is the total number of species, does not rise that quickly. It is called species area relationship. So you can also make a curve. What happens if you sample arthropods or other things from larger and larger area? Similar way how we did the curve when we were sampling more and more specimens or more and more samples. And this curve will actually look a little bit similar to that. Right? So it will rise very quickly in the beginning, but then once you reach some kind of critical area, you will not add that many species, but studying more and more and more. So that's why the estimate for the complete reserve, which is 6,000 hectares, is only 25,000. Only saying compared to the 72 millions, which you would normally get by the multiplying, but the number by itself, 25,000, is actually kind of super crazy. What else did they discover? So these things, based on 9 years of research, which somehow naturally looked at the arthropods and the fauna there more in detail, basically indicated that the estimates the estimates they did correspond quite well to the estimate which is based on the plant species, right? So if we do what Erwin did, something like multiplying the insects by number of plants, guessing that taking only the insects which we know that are specific for the plant, that are specialized for specific plant, then we can actually get quite correct number. The only important thing is that we need to have our guess how many species of insects and other arthropods are only specifically feeding on one plant. We have to have this number correct, right? Erwin had it too high. But if we use the correct estimate, the correct number, then estimate done by multiplying number of species living, feeding on one plant only by number of plants gets quite similar estimates, similar number of species than they get as they get for this reserve when they really actually checked all the species. Another important thing is that 1 hectare of tropical forest in Panama, so it's quite small area, it's this one rugby playground, actually can host more than 60% of the total diversity of arthropods in the larger area, in the complete reserve, right? This is actually quite important because it tells us that it makes quite good sense to protect remaining pieces of intact forest in lowlands, even if they are small, right? Naturally, we have to do more. It's not enough just to protect piece of forest. For many species, of arthropods, they need some minimum, or other organisms, they need some minimum area in which they can survive in the sustainable way and so on. But in general, if you have 1 hectare of good forest, still it's good to protect it, because it can still host lots of the original local diversity, right? And third thing, which is quite interesting, is that they compare this data for Panama with similar studies which were run in temperate zone. That means in the more colder areas in Europe mostly, right? So there were some studies done in France, UK, Italy, Czech Republic, or Azores, and the guess is that in the same area, so let's say 1 hectare, in the temperate zone, the diversity would be lower, right? So in Panama, the same area would have twice to 8 times, or twice to 8 times higher diversity of arthropods than somewhere in Europe. This will bring us to something about tropical diversity. We will talk about that the next weeks. So basically, why is that, right? Why in the tropics, in the same area, we have much more species? So how it is with Erwin number, the 30 million estimate now? Now we naturally have many more data, right? So we can actually return to his original idea, and we can test it with much more complete data we have now all over the world from all these places in the tropical forest where we do much more research now. And we can kind of guess how it is. So one of the paper which was published on that is this one. They actually did this published in 2010. They did quite similar way as Erwin. They also multiplied the number of insects which are specifically feeding on one tree, number of trees, and so on. But the difference is that actually they used models, and they used data from different places. Yeah, so they did not put there, okay, there are, I don't know, 160 beetles living in one tree. They knew that in New Guinea, in different trees, it's from, I don't know, 5 to 20. I just make up these numbers. In somewhere in Venezuela, it's something between 3 and 40, and so on. So they actually put there the ranges of for each number, for each value. They did not give one, but it's minimum and maximum. And they did some modeling on that. And thanks to that, they get some estimate, which is like the number which is most probable, but they also get some confidence interval, right? So for there, once they multiply these things, they actually got the estimate of number of tropical arthropod species, something like 6.1 million. And the range, because they have this confidence interval, was between something like 3.6 to 11.4 millions. So you can see that this range from 3.6 to 11.4 is far from 30. So now we actually know that the original estimate of 30 million of species done by Erwin in 1982 was actually too much. It was overestimating, right? There are actually more ways to kind of estimate the global richness. So this thing I have just shown you, that what Erwin did and these guys kind of recalculated using more data, are so-called empirical models. Then we can do something like study from local faunas. So that you can imagine that we can do something like what was done in the San Lorenzo forest, and then kind of estimate or extrapolate worldwide. Another thing we can do is we can ask specialists. So you can visit the guy working on some group of beetles, let's say, and ask him, okay, based on all the collections you have seen in the museums and all your lifelong work, how many species of your group you think it's living there? And then you kind of combine the data for all groups of insects and other arthropods, right? And then there are some kind of special new things. I will just show you one of them. This is a study published in 2015. So this study, for example, kind of considered some kind of expectation or idea that large species of arthropods are actually described and get their scientific names earlier than the smaller ones, right? Because they are easier to see. More people are interested in large things than in some super tiny things. So based in this way, you can put this in some kind of equation and you get some number based on the data we have. And for beetles, for example, they got some guess, some estimate that there are something between 1 to 2.1 million species of beetles. For insects, they got something like 5.5 million, right? For terrestrial arthropods, they got something like 6.8 million. Then there are some more studies specifically on insects. The latest paper is this one, published in 2020. They only cared about insects, so not all arthropods. They compared different ways how we can actually do the estimates, and they somehow concluded. So it's actually quite interesting to read if you are interested in this kind of questions. And they actually also concluded that there can be something like 5.5 million of insect species, plus some non-insect arthropods, right? They don't really care about that. So you can remember the previous slide is this one. It also said something like 5.5 million species of insects. So different studies using different methods nowadays, because we have much more data, actually start to show similar numbers, right? So we can already kind of more or less carefully trust these numbers to get some idea about total number of arthropod or insect species worldwide. Now you can kind of fool me like, okay, you like crustaceans and the marine things, and I did not really mention these things today at all, right? So why? So what we actually know about number of species of marine things, because we have seen in the previous weeks that they are actually also very diverse, right? You can find so many cool crustaceans and other things in the ocean. And we have also seen that arthropods actually originated in ocean. So we cannot kind of skip them. So how is the situation in the ocean? So there are not that many studies actually about that, partly because it's not that easy to study the marine diversity, not that easy to collect material. But the latest studies published in 2012 and 2017, which are this on the top right corner, they somehow use different methods. So they kind of use this method of the species accumulation curve, estimated the number of unknown species in samples. They also try to kind of take the rate of species description, so they know how many species are usually in each group described per year, and it's naturally kind of getting either quicker or slower, so this can be used for estimate. And they also include these opinions of specialists. So they ask, for example, the specialist for isopods, crustaceans, okay, how many of your isopods you think are living in the ocean? And based on that, they put together all the data. I put here some table with 7 groups of arthropods in the ocean, which actually are supposed to be the most diverse, right? So you can see that the most diverse by the number of known species nowadays are the copepods, which are this kind of tiny planktonic things. Which nowadays have 10,000 described species in the ocean, and the estimate is something like 40 to 60,000, so basically 4 to 6 times more. And if we go to the estimated number of species based by different methods, we would actually end up with the isopods to be the most diverse, right? So you can see that the estimate for the marine isopods is something like 60 something thousand to 120,000. So this can be the most diverse group of marine arthropods. And if you compare that to the number of known species, which is 6,300, you can see that there can be easily 10 to 20 times more of species which are still not known. And then there are some kind of unexpected things. So there's one thing which I mentioned to you very, very, very shortly as small group called Tanaidacea, which are kind of predatory crustaceans. And you can see that we only have something like 1,200 species, so that's why I did not really mention too much about that. But the estimate is that maybe in total they may have up to 60,000 species living in our planet, right? So sometimes actually the group which can be the very diverse one is not necessarily the one which has many described species. Maybe it's something which nobody is studying and we actually don't have that many species named in that group. So in total, if we kind of combine all this data, you can see that if you kind of sum up, we would end up with something like 180,000 to 350,000 species of marine arthropods, which still is much less than the 6 million, right? Which I mentioned for the terrestrial one. So there are actually much less species of marine arthropods or the ocean arthropods than the terrestrial one. That's the one of the reason is that arthropods actually one reason for their success was that they actually colonized the non-aquatic environment, the non-marine environment. That's why they have so many species. So that also means that most of their diversity is on outside of the sea. That naturally does not mean that the marine arthropods are not important. So the take-home message from all that concerning the number of species of arthropods worldwide is that we have something like 6 million terrestrial arthropod species living on our planet. Only 1 million of them has the scientific name, and naturally many of them only have the name, and we name them, we still don't know much about them. We don't know how they live, we don't know their lifestyle, we don't know their ecology and kind of connections to other organisms in the ecosystem. We don't know their distribution, for example. We don't know how the larvae are looking like, right? So this 1 million of known things does not mean that we know everything. We still need to study a lot of about them as well. And we know absolutely nothing about 5 million species of terrestrial arthropods. So we still need to work so much more to understand the group and understand actually our ecosystem, because naturally arthropods are a very important part of our ecosystem in the ocean also in the dry land. So we really need much more work on that. And the diversity of marine arthropods is smaller than those in the terrestrial ones, but it does not naturally mean that they are not important, right? We have seen some of the important, crucial parts of ecosystem, like the krill, for example, which is the food for the bigger things, including the whales. So the fact that they have less species in the sea, in the ocean, does not mean that they are not important. They also are very diverse in their lifestyles and very important for the marine ecosystems. Cool. So that's it. So please have some questions if you will not understand any part of this presentation. Just feel free to ask me next time and we can discuss about that. And somehow in correspondence to what we were talking about today is that we will go out to the forest probably the week after this one, for which you have this recorded lecture, and we will try to collect some arthropods by ourselves to little bit explore how many of them we can actually find, right? So we have seen that in some tropical forest reserve in Panama, they can find more than 6,000 arthropod species. So naturally we will not do study like that, but we can just sample a little bit and we can see how many different arthropods we can find in a super tiny sample from the forest around Kaohsiung. Cool. So see you next time, and feel free to ask me questions if you feel so.